Hello and welcome to today's lecture on horn antenna, which is in continuation of the previous lecture. So, in the previous lecture we have started discussing about E-plane sectoral horn antenna, and before that we actually looked into a rectangular waveguide and we saw what is the field distribution, and most of the time we operate these horn antennas in the fundamental mode, and we had seen that for a rectangular waveguide the field distribution is sinusoidal along the length A and it is uniform along B. And I had also mentioned about then when we talked about E-plane sectoral, when we flare in this particular direction, we saw that as you keep on increasing the value of B1, phase error started increasing and directivity started decreasing. But now let us just also look into the array theory concept of view. So, suppose now we have a field which is uniform over here. So, we can actually think about it as nothing but an array of this particular thing, and along this here field is varying sinusoidally. So, just think about from here to here. Let us look into the array theory. In array theory what we do? We have number of elements here. So, let us say 1, 2, 3, 4, 5, and here there is a sinusoidal variation. Now, in the array theory when we were talking about, I did mention to you that if the spacing between the element is reduced significantly, array factor for an array was given by sin n psi by 2 divided by n sin psi by 2. But if number of elements increase and the spacing between the element reduces, then that array factor reduces to the sinc function, which is sin n psi by 2 divided by n psi by 2. So, now for this aperture here what we can actually do, we can apply the array theory. Instead of calling array factor, now we call it space factor. So, we can see that since the field is uniform along this direction, so for E-plane radiation pattern, side lobe level will be given for the uniform distribution, and side lobe level for uniform distribution we had seen would be of the order of -13 to -13.5 dB. Whereas, in this plane here, since the field is varying sinusoidally and we had seen for cosine distribution, side lobe level is less than 20 dB, but of course gain will be also slightly less in this particular plane. So, we will remember this particular concept, and we talk about E field, then we will see these things here. So, now let us just very quickly go through what we had discussed in the last lecture. So, we started with the E-plane sectoral, we expanded in this particular direction, then we found out what is the phase error, and then we looked at the directivity curve, and we saw that as B1 increases, directivity increases initially, then starts decreasing, mainly because phase error is increasing in these particular for these particular values. And then we went through the derivation and we saw that delta max 90 degree is the value for which directivity is maximum. However, I also mentioned I do not recommend this much phase error, because this much phase error actually speaking reduces the efficiency of the antenna. So, we generally recommend phase error of about 45 degree. Then we had looked into the E-plane pattern in the previous lecture, we will just re-look into it. So, when the phase error, that means S is equal to very small value, which is 1/64 here. So, for that the phase error will be small and this will be the pattern, and you can actually see that this value here, if you draw the line here somewhere, so that is about -13 -13.5 dB. So, this is the pattern because E field is uniform along this direction, and that is why we have a side lobe level which is 13.5. But when we look at the phase error of 90 degree, one can actually see over here side lobe level is of the order of -10 dB, and that is definitely not desirable. Lot of power gets radiated in this particular direction, and hence overall efficiency of the antenna decreases. So, if we take delta max equal to 90 degree, typical efficiency may be of the order of 50% to 60%. However, if you take this value here where delta max is 45 degree, You can see for this particular case here, you can see that side lobe levels have definitely reduced from here to here. We can see little bit of a dip also. So that means radiation in this direction is much lesser than radiation compared to this particular value here. So naturally this will give us a better efficiency. So I generally recommend this one here, and we can get about 70 to 80% efficiency if delta max is taken around 45 degree. Now let us just look at the next one, which is H plane sectoral horn antenna. So what we do over here is that this flaring is done along the H plane. So we know that this is E plane, H plane is in this direction. So the flaring is done in this particular direction here. So in the previous case, B was expanded to B1, here A is expanded to A1. Now as far as the field variation is there, it will remain same as before, except that earlier it was expanded in this direction, now it will be expanded in this direction here. So we can actually see EY, that will be the component in this direction. So this EY, let's amplitude is, let's say E2, and the variation is given by this particular term over here. Again, when x dash is equal to 0, which is the origin, so at this particular value cos 0 will be equal to 1, so we will get a maximum value, and at x dash equal to A1 by 2, which is at the edges over here, this will be A1 by 2, that means it will become pi by 2, cos pi by 2 is equal to 0. So that is the field distribution along this here. So here again, if we look at it, the phase error, if we take this as a reference point, then the phase error will keep on increasing, and the maximum phase error will be obtained when x dash becomes equal to A1 by 2. In previous case, it was y dash equal to B1 by 2, because flaring was done along this particular direction. So here also then similarly we can write delta max. So just to differentiate the notation, instead of S earlier we have written here T, and rho 1 becomes rho 2 and B1 becomes A1 over here. Otherwise the concept remains the same. So if we look at the directivity curve, we see a very similar trend. So what we have here, again now this is the normalized value of the directivity, because the dimension B is not changing, so it is normalized with respect to that and wavelength, and over here dimension A1 is changing, so that means aperture size is increasing in this particular direction. And what we have here, the length of the horn antenna is increasing. So from here to here you can see there are different cases. Here the length is 100 lambda, which would be very large compared to this, which is about 6 lambda. Just think about it, suppose you are designing an antenna at say 3 gigahertz. So at 3 gigahertz wavelength will be 10 centimeter. So if it is 100 lambda, that would mean this whole length is going to be 10 meter. So you can imagine it is a very long antenna. Okay. At the same time, if we think about 3 gigahertz, lambda is 10 centimeter, this would imply this is about 60 centimeter, which is actually equal to 2 feet long. And now this dimension is increasing. So we can actually see that as you go over here, the directivity increases and then it starts decreasing. Same thing is followed just as before. So here again, if you look at the point where this is a maximum directivity, so corresponding to again 6 lambda, if you now draw the line, this is about 4.24, and if you go over here for 100 lambda, if you draw the line somewhere here, it is about 17.32. If you recall, earlier this number was about 14.14 for the E plane sectoral, whereas for H plane sectoral it is 17.32. And if we do the line draw from here, if we draw from here a curve which goes through the center, so that will be like an equation which is given by this particular expression. And now you might wonder why these things are different. Let me just cover the next slide and then I will explain why these numbers are little higher compared to the previous case. So if we use this particular expression, we can now find out maximum directivity we just saw is given by this expression. we know maximum phase error occurs when x dash is equal to a1 by 2. So, we know delta max 2 pi t, where t is this. So, now let us substitute the values. So, t we put over here, and here what we are going to do for maximum directivity, we know a1 should be this. So, if we substitute the value here, t optimum comes out to be 3 by 8, and if we put the value of 3 by 8 here and pi we write in 180 degree. So, 2 into 180 into 3 by 8 gives us 135 degree phase error. And again, this is my recommendation that please never ever use this much phase error is too high, not recommended. So, now the question comes, why in the previous case we allowed the phase error of 90 degree for E plane, and why phase error of 135 degree is allowed for the H plane. And the reason for that is that for E plane, what is happening, field is uniform over the entire region. So, if you look at the center point where the phase is 0, that is a reference, and if you look at here, this entire amplitude, let us say, goes to 90 degree, and that is not doing any contribution. But now if you look at an H plane, so in H plane what is happening, field is varying sinusoidally. So, maximum here and it is 0 over here, and when we expand this whole thing, so what happens, maxima is also getting expanded, whereas end points are 0. So, at 0 level there is really no difference, contribution will not be there. Hence, we can tolerate little larger phase error because amplitude is going to 0 at the end. So, even if that 0, even if that is pointing in the other direction, still the middle portion is getting expanded, which gives rise to larger directivity. So, theoretically we can say that maximum directivity is obtained for phase error equal to 135 degree. I will tell you my reason also why I do not recommend this value. So, again just look into this here. So, even though at this particular point we say that phase error 135 degree is allowed, but just if you draw the line from here corresponding to this point, had the phase error been 0, instead of getting this value over here for the directivity, it would have gone vertically up and would have gone here. So, it could have been this much directivity, which would have been much larger compared to this here if the phase error was relatively small or negligible. So, hence I do not recommend phase error of 135 degree at all, and we will see later on what are the implications of these things. But let us just now look at the radiation pattern, which is known as a universal radiation pattern for H plane. What we have here, normalized field in this direction, and this is actually nothing but we are showing the values of A here, and these are the different curves for different value of the phase error. So, this one here, let us start with here, this corresponds to the very small phase error. You can see that this is a factor is much smaller over here. And now let us just see this particular here. If you look at the side lobe level, that if I draw the line here, you can see it is much below 20 dB. So, in fact, if you recall now, for uniform field distribution, we saw the side lobe level was much higher, that was close to 13 dB, but if it is a cosine distribution, side lobe level are of the order of minus 22 dB or so, and these things are very similar to the array theory, which you convert to space factor over here. So, now corresponding to this here, what do we see? So, here phase error is very, very small. This is the curve for which you can see that the phase error is 45 degree, and then we see this curve here. This is the curve for phase angle error equal to 90 degree. If you see over here compared to this, you can see that the amplitude has increased significantly. That means much more power is being radiated in the undesired direction, and in fact 135 degree phase error will come somewhere in between this curve and this curve here, because this is 1 by 4, this is 1 by 2, and 135 degree corresponds to 3 by 8, which curve will be in between here. So, you can see that radiation will be taking place in the undesired direction, and hence overall directivity of the antenna decreases. So, when you are going to design a horn antenna, please remember, for E plane sectoral horn antenna, try to design for a phase error of about 45 degree. For H plane sectoral horn antenna, I can recommend anything between 45 degree to 90 degree phase error, depending upon what are the requirement for the given application, but do not take beyond that. So, now we will see the combination of E plane sectoral and H plane sectoral, and that is known as pyramidal horn antenna. So, let us just look at the pyramidal horn antenna. So, in the pyramidal horn antenna, the expansion is done in both the plane. So, this is also expanded, this is also expanded. So, this is the side view, you will see only this portion which is over here, and the top view, if you see, that will be this part here. So, top view we are seeing from A, and this is the expansion over here. So, now if you look at the field distribution will actually have the similar amplitude distribution, because the field variation is only in the one direction, which is a cosine distribution. Again we can put it, if x dash is equal to 0, cos 0 will be 1, so that will be E0, and at x dash equal to A1 by 2, this will be pi by 2, which is equal to 0. But however, if you see the phase error has increased much more now, because what you see now, that the phase error now is the sum of the two phase errors. So, in one time what we are doing, we are going in the, let us say, in A direction, and then we are going in the B direction. So, the phase error will be much more over here for pyramidal horn antenna. And then comes the next part, condition for physical realization. In fact, actually there is only one condition, even though you see here 3 equation. The actual condition is that PE should be equal to PH, where P is given by this and PH is given by this expression here. So, let us see what are these things here. So, if you look into here, so we actually call it distance from here to here is actually known as the distance from aperture. Aperture is also referred sometimes in books as the mouth of the horn antenna, and this one over here is known as neck of the horn antenna. So, we actually what we are looking at here is the distance from here to this point. So, that is the, you can call it a neck, and this is the mouth. So, neck to mouth distance for this case as well as for this case should be same. Now, I want to mention here a few things here. So, it is this distance from here to here and this distance from here to here, that should be constant, whereas what we were earlier looking at is the phase center. Now, phase center for this particular case is different than the phase center in this case here. The reason for that is, here the flare angle over here may not be same as flare angle in this particular direction. The reason for that is, we can actually have a larger phase error in the H plane, and we can have a lesser phase angle error in the E plane, because the amplitude is uniform along this. So, that is why, since the flare angle will be different, phase center will be slightly different in the two cases. However, for physical realization, from here to here and from here to here, it should be same. So, we can just say it looks like a P, but actually it is a rho E and rho H. So, rho E and rho H should be same. Now, how do we calculate the expression for rho E? So, I just want to mention, I will give you some hint here. So, now let us say this is the angle here. So, for this particular angle, if you look at this part here, one triangle, and you need to imagine this as another triangle. Tan alpha is given by this distance divided by this distance here. So, this distance is nothing but B1 by 2 divided by this distance here, which has been taken as rho 1. Also, the same thing can be written for this here, that this tan alpha of this will be this distance, which is B by 2 divided by this distance here. Okay, so, that gives one expression. and now we know that distance from here to here will be nothing but rho 1 minus this particular distance, and this distance we have seen that tan of this angle will be b by 2 divided by this. So, simplify this equation for this term which is rho e. Similarly, you do the same thing, simplify it for the term here rho h, and then put this condition over here, and these are the expanded thing. You can see that basically these terms are coming. As I said, you need to just do a little bit of a calculation, use that concept of tan angle, and then take the two ratios, simplify it, you will get this particular expression. So, this is the only condition which we need to put for physical realization. So, now we need to design, let us say, a horn antenna. For designing a horn antenna, there are two important things which we need to know. First is, what is the frequency at which we are going to operate. It is very, very important to know at what frequency we are going to operate horn antenna, because we know that, let us say, a rectangular waveguide will be expanded to pyramidal horn. So, we must know what is the cutoff frequency of the rectangular waveguide and what is the operating frequency range of the waveguide. Until unless we know that, we cannot just choose arbitrary. So, for example, we had seen that for X band, which is from 8.4 to 12.4, so any frequency in that particular band 8.4 to 12.4, we can design pyramidal horn antenna in that frequency band, and for that we need to take WR 90. Similarly, suppose you want to design antenna at say 30 gigahertz, or you want to design antenna at 1 gigahertz, you must choose proper waveguide which will have that operating frequency range. Then comes the next part. Once frequency is given, so we choose the waveguide dimension. The next part will be, we need to design horn antenna for a given gain or directivity. There are two possibilities are there. I have given the directivity curve for E and H plane, which were the normalized E and H plane. So, we can use that to find the overall directivity of pyramidal horn. So, if you look into this here, so we saw the normalized plot which were lambda dE by one of the term here, and then lambda dH by the another term. So, this part is actually already known from those two directivity curve, and then we can find out what is the directivity. Alternatively, we can find the directivity of the horn antenna from its aperture. So, what is the aperture? So, aperture area theory, if we apply, it says 4 pi area multiplied by lambda square, and at the aperture, what is the area of the aperture? A1 multiplied by B1. So, if you look at the directivity expression over here, the length of the horn antenna does not come into picture, right. So, one may think that, well, directivity is independent of the length, but that is not the correct thing, and we can see here that the gain of the horn antenna is almost half of this particular value. If you look into there, this means that the efficiency of this particular antenna is only 50%, and I actually want to mention all those optimum dimensions which we had seen, they really give rise to an efficiency of only about 50%. But I also want to mention that some books do take, instead of 0.5, they take as 0.6 also. So, some books take this 60% efficiency, some people or some books take 50% efficiency, but we will show you much later how to get even better efficiency. But right now I will go with this textbook approach, and we will see how things can be simplified and designed. So, now we had seen for a optimum pyramidal horn antenna, for first we had looked into the sectoral. So, we had seen for E plane sectoral, this was the optimum dimension. For H plane sectoral, that was the optimum dimension. Now, again here an assumption has been made that rho 2 is approximately equal to rho h, which is not always true. This will only happen if the aperture size is relatively small compared to the length of the horn antenna. And when we talk about the length of the horn, the length is actually taken from the neck to the mouth. And this we had seen, these are the values of the rho e and rho h. These values, as I mentioned, these have been obtained for the physical realization of the horn antenna. Now what we have here, equation 1, 2, 3, 4, 5. If you combine these equations, and by combining these equations, one actually gets equation over here. Now that may look like a fairly complicated equation over here, but just 3-4 steps it will take for you to combine the equation. You can actually just see here what needs to be done. So we have a A1 B1 here. So now A1 B1 is given by this particular term over here, and this term has been approximated by this here. So these term over here, you can actually take square of this everything. So A1 square B1 square, square root will get rid of it, and then this term here is given by the term over here, and this one comes over here. So you can actually see that all of these things will come in this particular expression. Okay, and then what you can see over here, that term xi, or you can say x also for simplicity. If you see here, x is in the numerator and over here x is in the denominator. That is how it has been arranged, and where the expression x is, it is nothing but rho e divided by lambda. You can see that. So now what we need to do it is, we need to solve this equation for, I will just use the term x here even though this is known as xi. So we need to solve for x, and for that what we need to do, we need to start with the trial, and this is the good trial equation. So if you try with this equation, it is possible that this left hand side may not be equal to right hand side. So you may have to do some trial. So I am just going to just show you very quickly, but in the next lecture I will show you more detail. So if you calculate this from here, the trial value, then you can calculate rest of the parameter. There are some design equations are given. There is a design for 11 gigahertz is given for a given value of the gain over here. So that is the solution. I am just very quickly going to show you the trailer of the next lecture. So you can choose starting value of x, then you do this, you do all of these calculation, and finally you can do the design. Alternatively, if you actually read the cross book, in the cross book this graph is actually given over here. So for any value of the gain which is over here, draw the vertical line and read the corresponding values, design is over. Okay, so it is a very simplified way of doing the thing. However, I want that you people look into the derivation from this part. First I would like that you people do some practice, derive this particular expression for this condition, and then derive this particular expression from the previous equation, and in the next lecture we will continue from here. Okay. So with that, just to quickly summarize, so today we restarted with the E-plane sectoral horn antenna. We looked at the field distribution, and we saw that for very small phase error, the side lobe level will be of the order of -13 dB or so, but as the phase error increases, side lobe level increases and efficiency decreases. Then we looked at the H-plane sectoral horn antenna, and we noticed that because of the cosine distribution, side lobe levels were below 20 dB and phase error can be little larger compared to the E-plane sectoral antenna. And then we talked about the pyramidal horn antenna, and there is a one main condition for physical realization. You can say that for E-plane sectoral or H-plane sectoral, the length from the mouth to the neck should be same. And then I showed you the equation, and very quickly I showed you how graphically you can solve the problem also. But in the next lecture we will see these things in more detail. Till then, bye, do some practice, because as they say, practice make man perfect. I still do not know why they don't say practice make woman perfect. In fact, I said that sometime, and one lady responded that women are perfect, so why mess with the perfection, okay? But I would like to say practice make people perfect, okay? So please do some practice, read these examples from the book, and we'll continue from here in the next lecture. Till then, bye.